When we have a vector, we say that it is made up of horizontal and vertical vector components. And these vector components, or projections, actually come from our unit vectors that are multiplied by a scalar value. We call these scalar values scalar components, or unit vector components, because we can define any vector with these numbers, since they correspond to our vector components. Another way we can define vectors is by their magnitude and the angle they make with the x-axis. When we have a vector defined this way, to find the scalar components, we multiply its magnitude and the cosine or sine of the angle it makes with the x-axis. Thanks to the properties of these trigonometric functions, we get the correct scalar component, even if it's an obtuse angle. The dot or scalar product is a vector operation defined as a product of magnitudes of two vectors and the cosine of some angle theta between them. Multiplying the magnitude of a vector and the cosine of an angle is actually very familiar from the scalar projection idea. Here, instead of doing scalar projection on horizontal or vertical axes, we do it on the axis that goes through the B vector, and what we get is a scalar projection of A onto B, meaning that if we multiply this value with the unit vector in the direction of B, we will get the vector projection of A onto B. So, the dot product is actually the product of one vector's magnitude and the scalar projection of the other. The dot product of two vectors gives us a scalar result. Thanks to the cosine in our formula, the result gives us an idea of how our vectors are relatively oriented. In other words, how much they point in the same direction. If the result is equal to the product of the magnitudes, then the vectors are pointing in the same direction. In other words, parallel. If the result is product of magnitudes times -1, the vectors should be anti-parallel. In other words, pointing in the opposite direction. If the result is 0, then the cosine of the angle between the vectors must be 0, which means the vectors must be perpendicular. Additionally, the result will be positive if the angle is acute, and negative if the angle is obtuse, due to the sign changes of the cosine function. The dot product also has some important properties. First property can be explained by the fact that the angle between identical vectors will always be 0. Second property can be understood by looking at our formula and seeing that the order of the vectors make no difference. Third property is called the distributive property, and since it's less trivial, I'll explain it last. Fourth one can be understood by looking at our formula and seeing that scaling either of the vectors by a value will scale the result of the dot product by the same value. Fifth one comes from the fact that a zero vector has zero magnitude, and looking at our formula, we can confirm it will always make the result 0. To understand the distributive property, let's remember how we interpreted the dot product. The dot product is the product of the magnitude of one vector and the scalar projection of the other. Now, we have vector A and vectors C and D that add up to make vector A. What's important to see here is that the vector projections of C and D sum up to the vector projection of A. Since the scalar projection is just a way of representing a vector projection with a scalar value, scalar projections of C and D also sum up to the scalar projection of A. Now, it's obvious that we can distribute the brackets. And now, we can see that the sum of these two dot products is equal to our original dot product. So far, the formula we use to define the dot product is called the geometric definition. The other definition is called algebraic or component definition. This second formula is very important as it allows us to calculate the dot product by using the unit vector components of the vectors without having to know or calculate the angle between them. Moreover, Using the two definitions together allows us to find the angle between two vectors that we know the components of, since we can calculate the magnitude using the components. We first calculate the dot product using the algebraic formula, then calculate magnitudes of each vector, then we find the result of cosine theta, and using inverse cosine we find theta. However, there is a problem. Where the component formula comes from and why it gives the same result as the geometric formula is probably the least understood part about learning the dot product. When taking the dot product of vector A and vector B, we can apply the distributive property, since the vertical and horizontal components of A add up to A, meaning that the projections also add up to A's projections. Now, instead of the dot product of A and B, our expression becomes two dot products, one for each component of A. And then, we also apply the distributive formula on both of these dot products, since B is also made up of vertical and horizontal components. The sum of the four dot products we now have is equal to our original dot product. Now, since two of these dot products involve one horizontal and one vertical component each, they are always going to result in 0. The other two dot products are always going to be parallel or anti-parallel, therefore their value is going to be equal to the products of the corresponding scalar components. This is because these scalar components are just scalar projections on the coordinate axes, so they are just magnitudes with a sign, making the result correct even if they are anti-parallel.